All right, welcome and thanks for joining section 2.1, so starting chapter 2. Chapter 2, we get into a lot of different sketching, particularly quadratic and rational functions. So we start off nice, we're talking about quadratic functions. We're going to talk about mainly the sketching of them and then just some terminology and some vocab words that we definitely need to know. So starting with a polynomial function. When we're talking about a polynomial function, we say let n be any non-negative integer and let this is going to look a little bit visually overwhelming, but it's not that bad. A sub n, comma, a sub n minus 1, comma, and then we're just going to do dot, 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 meaning there's an infinite number of things that can happen in between here. And we'll have a sub 2, comma, a sub 1, comma, a sub 0. It's a comma, this is a 1. B, real numbers with a sub n is not equal to 0. So this is just talking about terms in a sort of sequence or series. A polynomial function can then be given by f of x is equal to a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1 plus so on and so forth plus a sub 2x squared plus a sub 1x to the first plus a sub 0 x to the 0. And keep in mind that anything to the 0 power is really just 1. So this is actually just a number that doesn't have an x. This is called a polynomial function of x, since x is the variable here. So a polynomial function of x with degree n. And just sort of talking about what all of this is really saying is just n must be a non-negative integer, and a sub n must be real numbers. So we're saying that our exponents, since they must be non-negative integers, our exponents cannot be fractions, so no types of roots or radicals, and they can't be negative, meaning x cannot be in a denominator, because that would come about from a negative exponent. The coefficients of x must be real numbers, and your lead real number cannot be 0. That would change the type of function. Anything that meets those requirements would be a polynomial, or what's classified as a polynomial. So we're thinking right now, this non-negative, if I have a rational expression with x in a denominator, that's not a polynomial. Or if I don't have an integer, if I have some type of root, square root, cubic root, it's not a polynomial function because it has a fractional exponent. So polynomial functions are classified by degree. And when we're talking about the degree, what we're talking about is the highest power of x. So for instance, if we're talking about the constant function, for the constant function, we have f of x is equal to a sub 0 x to the 0. So this is our constant function. That's something like f of x equals 10, because a sub 0 would be 10, and there's no x. Or something like y equals 3. That's a constant function. It's a horizontal line. This is such that a sub 0 cannot be equal to 0. The degree here, our degree would be the 0 power. That's sort of a, not as interesting case. The linear function, so if we have f of x is equal to mx plus b, this is such that, m is not equal to 0. If m were 0, we would have a 0 for this whole term, and it wouldn't be a linear function, it would be a constant function, because you'd just have f of x equals some number. The degree here would be equal to 1, because that's the highest power of x. Here, my highest power of x was 0. And then we get to the quadratic function, and this is what we're going to be sort of looking at for the section. We have f of x equals ax squared plus bx plus c, such that a is not equal to 0. And the only reason I'm writing this is to keep in mind, if a were 0, this wouldn't actually be a quadratic function because you just have this bx plus c, which is linear. The degree of this, the highest power of x, so the degree here is 2. The degree of a polynomial is what tells you what type of polynomial it is. So, since we're talking about quadratics, the shape of this is going to be a parabola. One common thing that people just, verbiage say wrong, when I ask like what type of function is this, it's a quadratic function. The shape of it is a parabola. So a parabola is not like the type of function. You mean the right thing, but you're saying the wrong thing. When we talk about the vertex of a quadratic function is always going to be the min or the max. And that's found by doing negative b over 2a, comma f of negative b over 2a. Although we don't use that as much, what we're going to use more is h comma k. And that just has to do more with the form that we're going to be working in. The axis of symmetry is the vertical line through the vertex. So it's a vertical line going through the vertex, and it's always in the form of x equals whatever that h value is. So that's just some, a little bit of background on quadratics. When we're talking about parabolas, they can either open upwards or downwards. So parabolas have a direction. If a is greater than 0, so if a is positive, then the parabola opens up. And if you wanted a little idea, okay, this is a parabola that opens upward. Another way of thinking about that is just that the vertex is the minimum. So if a is positive, the vertex is going to be the minimum. If a is negative, the parabola opens down. And if you want an idea, okay, this is a parabola that opens down. And what that means is that the vertex is a maximum. So the value of a ultimately leads to any reflections over the x-axis. Because if a is positive, we just have a regular parabola. If a is negative, what's happening is I'm reflecting this, throwing back to 1.4, I'm reflecting this downward over the x-axis. We don't have any reflecting over the y-axis in this form. If I were taking, some piece of this parabola and flipping it over the y-axis, it would just be the same parabola. And that's why we don't really have reflections over the y-axis. And you could sort of prove that algebraically as well. But just know that, A is really telling us about reflections as well as stretching and shrinking. So talking about stretching and shrinking, if A is greater than 1, and more so if the absolute value of A is greater than 1, then the parabola is vertically stretched. Remember that when we're talking about stretching and shrinking, with things that are vertical, they're not counterintuitive. So if I have an A value that's like 7x squared, that's a vertical stretch. If the absolute value of A is between 0 and 1, then the parabola is vertically shrunk. And I will, vertically, that was spelled terribly, shrunk. Remember, if A is less than 0, the negative is just telling me that there's a reflection. The actual value between 0 and 1 or greater than 1, that's telling me the stretch or shrink. In this form, just like with reflecting, there is no horizontal stretching or shrinking. You don't have horizontal stretching or shrinking in this form. Standard form. Standard form, also referred to as vertex form, because when you're in standard form, you can see the vertex right away, is written as f of x is equal to a times x minus h squared plus k. This a value tells me two things. It tells me if there's a reflection, and it tells me if there's a vertical stretch or shrink. This form also helps us realize any shifting, because h and k, those would represent two different types of shift. Here I have a horizontal shift. Here I have a vertical shift. And the actual value of h and k are going to give me the vertex of the parabola. So vertex form is sort of that thing that we're going to be using a lot, sort of more frequently. We'll do a couple examples over in that example video if you want to stop on by, watch that, listen to my voice a little bit more. But we're on slide 8 now, talking about x-intercepts, just a little bit more background information about parabolas. So x-intercepts are values for x for which the function is 0. So values for x for which the function is 0. Or, in math terms, it's when f of x is equal to 0. So those are our x-intercepts. Those are the points on the graph in which the function, in this case, a parabola, or a quadratic function, which looks like a parabola, crosses the x-axis. So if I have f of x equals x squared minus 4, I would have 0 equals x squared minus 4, and I solved this. So I'm going to have 4 equals x squared. So x equals plus or minus 2. Don't forget that plus or minus. So these are x-intercepts. What I know about every x-intercept, just the nature of what it is that the y value must be 0 because it's on the x-axis. And what I did here is I just got, okay, positive 2 is an x-intercept, negative 2 is an x-intercept. If I wanted to sketch this to sort of give me an idea, 2, 0 is an x-intercept, negative 2, 0 is an x-intercept. If you wanted, you could even talk about the y-intercept. Y-intercepts are when I substitute 0 in, and what I get here is negative 4. You could also talk about the vertex. If this is in standard form, h is the thing in parentheses with x. I don't have it on that previous slide. H is the thing in parentheses with x. So in this case, there's nothing there, so it's 0. K is whatever's been added to the squared, so k is negative 4. So our vertex, 0, negative 4, same thing as our y-intercept here. And I have this parabola going through. And I missed that point, so I'm just going to move it over and act like it didn't happen. Cool. All right. Everything else that we have here is just examples. So, this is very introductory, but I really hope that you do go and watch that optional video. In that optional video, I do a lot of the examples, and you see a lot of like factoring and completing the square, some really cool things that you definitely want to hear and get some practice on. If not, you'll pay attention to it in class, and we'll get through all of chapter 2 soon. Thank you.